In this video, we explore an important concept of computer science, recursive function. The concept of recursion is a challenging concept which sometimes inspires fears among students. For some, it is a natural way of thinking, and they will find the concept almost trivial. Whereas for others, it will take more time. Don't be discouraged. After some effort, you will find the concept rather elegant and intuitive. What is recursion? Should be the first question we should answer. Perhaps the best way to approach the question is via an everyday example. Let's consider the problem of finding my position in a queue for the premiere of the latest Star Trek movie. With the programming techniques we know so far, we will use an iterative approach. I'll ask my friend to keep my spot, and I will walk toward the front of the queue and store on a piece of paper, my variable, the number of people I passed by. Once at the front of the queue, I have my answer. Gosh, that was a long queue and I'm exhausted. Being on the lazy side by nature, I promised myself to have a better, lazier approach to find out my position in the queue for the next Marvel movie. I am changing the paradigm. I am breaking the problem down into sub-problem. If I think of it, my position is the position of the person in front of me plus 1. So in order to find my position, I ask the person in front of me what is her position. The person in front of me does not know its position. So the person asks the person in front of her or him. This process continues until we arrive at the person at the front of the queue. Arriving at the person at the front of the queue is a stopping condition. That is, we don't need to ask the position of another person. The person at the front of the queue knows its position, which is first or 1, and can reply to the person behind her who just asked for her position. That person now knows its position, which is 1 plus 1 equals 2, and can communicate its answer to the person behind her. This feedback continues until I have my answer. And it turns out that we can model this problem with this simple blueprint. We ask the first question: what's the least amount of work that I can do? How do I break this problem down into some sub-problem? In our example, my position is the position of the person in front of me plus 1. And the second question that I have is, when will the process complete? Like, what's my stopping condition? In our example, it's when we hit the first person in the queue. This problem can be written with a very minimal algorithm. Function, get position in queue, p a person, and return an int. If nobody in front of p, then return 1. Else, return 1 plus get position in queue of p dot person in front. The case nobody in front of p is the simplest case, the one with the least amount of work, as we can reply directly that the position is 1. This is our base case. The else statement represents more work that needs to be done. This is our general case, where the problem is decomposed into sub-problems. Note how our general case calls the function itself. This is the recursive step. Now that we have some sort of understanding of recursion, we could look at a more formal definition. In mathematical logic and computer science, recursive definition or inductive definition is used to define an object in terms of itself. The definition of Excel may seem obscure at first, but it will become clearer later when we talk about function and recursive data structure. Excel definition can be read as follows when we consider only the case of a function definition. A recursive definition of a function defines the value of a function for some inputs in terms of the value of the same function for other, usually smaller, inputs. A function exhibits recursive behavior when it can be defined by two properties: a simple base case, or base cases, we may have more than one, and a set of rules which reduce all other cases towards the base cases. Before we move on to an example of recursion, we need to explore a topic that is often overlooked when teaching recursion: the call stack. It is a fundamental concept that you really need to grasp to understand what is so magical about recursion. To see how call stack works, let's take a look at this simple program here. We have three functions, where A has a dependency on B, and B has a dependency on C. The call stack is an abstraction that our operating system leverages to store function invocation within our program. The call stack stores stack frames. A stack frame is a memory management technique used in some programming languages for generating and eliminating temporary variables such as parameters that were passed onto the function call. In other words, it can be considered the collection of all information on the stack pertaining to a subprogram call. When executing A, the stack frame is added to the call stack. When the call is completed, the stack frame is removed from the call stack. However, in order to complete the function A, we need to call B. Another stack frame is then added to the call stack. Similarly, in order to complete the function B, we need to call C. Another stack frame is added to the call stack. At this time, we have three frames in the stack. The function C does not depend on any other function and returns a value. At this stage, the return value is passed to the function B, and the stack frame for C is removed from the call stack. Now, B can terminate and it returns a value. The return value is passed to the function A, and the stack frame for B is removed from the call stack. Finally, A can be completed, the result is printed, the stack frame for A is removed. The program finishes. Now let's consider a function A that calls itself. For example, a recursive function to sum all positive integers up to n. It can be written as def A of n return A plus a n minus 1. The problem can indeed be expressed in terms of its subproblem. The sum of the n first positive integer is the sum of the n minus 1 first positive integer plus n. Now let's call this function with n equals 4, which should return 10. The first stack frame is for the call A4, which call A3. Another stack frame is created for A3 and is added to the call stack. Then A3 calls A2. As you can see, our subproblems are getting smaller. In other words, are getting closer to 0. The recursive calls continue, and at some point, we arrive at A of minus 1. At this stage, we realize the program will execute forever. We keep adding frames to the stack until we have a stack overflow error. This exception happens when we exceed the pre-allocated buffer of memory that a program has. In other words, the program has run out of memory. Believe me, you will get that error quite often, even when you get more experienced. The function was missing a stopping condition, what we have referred to as a base case. Without the base case, the recursive call will continue until the program runs out of memory. When you see a stack overflow error, your first instinct should be to check for a missing base case. In fact, the code should have been def A of n if n is equal to 0, return 0, else return n plus a of n minus 1. I have added the variable output for pedagogical purpose. So you can see all the stack frame being removed from the call stack. Now that we have debugged our code, let's have another go at it by calling a of 4. Every time a recursive call is made, an additional stack frame is added to the call stack. In the variable frame, the value of n are decreasing. Notice also that so far, the local variable output is not present. This is because the right-hand side of the assignment operator is evaluated first. And so far, we have made successive recursive calls, but we have not yet reached the base case, and no value has been returned. Once we arrive at n equals 0, we can see one of the stack frame being removed. And in addition, in the stack frame for n equals 1, we have the local variable output initialized with the value 0. One by one, the stack frames are being removed from the stack, and the output is being updated until we obtain the desired result. Let's have another example. The factorial function factorial n is defined by the rules factorial 0 is equal to 1, and for all n greater than 0, factorial n is equal to n times factorial of n minus 1. Factorial 0 is the base case, and then the next rule is the general case. Recursive approaches rely on the fact that it is usually simpler to solve a smaller problem than a larger one. Take for example factorial 4. Factorial 4 can be expressed in terms of factorial 3, which is smaller, simpler in a way. Similarly, factorial 3 can be expressed in terms of factorial 2, and so on, until we reach the base case factorial 0. It is then possible to compute the desired solution. Let's look at two possible implementations of the factorial function. Let's implement the function factorial recursively first. We define a function factorial underscore rec with a parameter n. Let's use the general form given by the mathematical definition of factorial, that is, to return n times factorial of n minus 1. Having finished that implementation, I need to check if it returns the expected result. So let's print the factorial of for example, 4, which is 24. Let's save the file and execute it. Clearly, there is an issue here. We have a maximum recursion depth exceeding error. What's happening here? This is a Python equivalent of the Stack Overflow error. The program ran out of memory before it managed to compute the result. In other words, the program kept making recursive calls until it ran out of memory. The most likely cause is a missing base case. Let's have another look at factorial, but this time using the debugger. As you can see, n decreases to 3, then 2, then 1, and 0. However, when I have n equals 0, I do not stop the recursive call. In fact, I'm calling factorial of minus 1, instead of returning the value 0. And the recursive call continues with minus 1, then minus 2, and so on. It never stops. I have forgotten to implement the base case. Remember, in the definition of factorial, we have the base case factorial 0 is 1. In my code, I need to add the statements if n is equal to 0, then return 1. There is no more recursive call. Let's run the program again, and this time I have the expected result of 24. Of course, one of the preconditions is that n is a positive integer. If someone calls the function with a negative n, the program will crash. However, in that case, the developer did not respect the precondition that n should be a positive number, and therefore it is their responsibility to correct their code, not mine. I have implemented factorial using a recursive function, but I could have implemented it using an iterative implementation. To distinguish the two implementations, let's call that function factorial underscore iter for iterative. The next step is to initialize our accumulator output to 1. Then we need to use a for loop for I in range 1 to n plus 1 in order to include n, output times equal I. Then I just need to return output once the loop terminates. Let's run the program to check that both implementations return the same result of 24. As you can see, I can implement that function either recursively or iteratively. But if you look at the recursive function, the implementation is much closer to the mathematical definition, whereas the iterative implementation doesn't show any similarity with the mathematical definition. It will be much harder to prove the correctness of the iterative implementation, and it will be much harder to understand the implementation given the mathematical definition. I agree, for such a simple problem, it does not matter much. However, you will encounter more challenging problems where a recursive implementation will feel more natural and easier than an iterative one. In this example of computing factorial 4, we can see that we are making successive recursive calls until we reach a base case. Each line represents a call stack where a new stack frame has been added. Once we reach the base case, we can return the result of each recursive call, removing the completed stack frame from the call stack, which will reach the first function call and return the computed value. You can notice the triangular shape of the successive call, which is quite common in recursive function. In this video, we have seen the concept of recursion. I have also introduced the call stack and stack frame, which is a fundamental topic when considering a recursive implementation of a function. We have also explored some of the issues that may arise when implementing a recursive function, especially when we are missing a base case. But there is more. In our next video, we will be looking at some of the issues associated with the performance of recursive algorithms, which look at the pros and cons of using recursion when solving a problem.